friends, welcome back. And in the last lecture we started with the classification of glycosides, and we discussed the classification of glycosides on the basis of the atom or the glycosidic linkage that is formed between the sugar or the glycone part and the A-glycone part. So now we will discuss about the classification of the glycosides on the basis of the type of the A-glycone that is attached to the sugars. So as I told you that the A-glycone part can belong to any class of secondary metabolites, so we can say that the glycosides on the basis of the A-glycone moiety can be classified into anthraquinone glycosides, steroid glycosides, which are also known as cardioactive glycosides, then flavonoid glycosides. We already discussed these type of glycosides when I discussed about flavonoids in my lecture. Then coumarin glycosides. We discussed coumarin glycosides lecture wherein I gave an example of scopolamine, which is a glycoside of simple coumarin, that is scopolamine. Then we have cyanogenetic or cyanophoric glycosides. Now these are the glycosides which on hydrolysis gives you hydrogen cyanide. Then other classes are of saponin glycosides. Now saponin glycosides are those glycosides which have soap-like characters, and therefore the name saponin is given. So whenever these glycosides are mixed with water and are shaken, they produce froth soaps. Then alkaloidal glycosides we have, or glycoalkaloids we have discussed when I discussed about alkaloids. And if you want to have an example of alkaloidal glycosides or glycoalkaloid, and most common example is solasodine, which is found in different species belonging to genus Solanum. Then iridoid glycosides are the bitter glycosides, and you can find these iridoid glycosides in the species of belonging to genus Schwarzschiia, or belonging to genus Gentian or Andrographis, and so on and so forth. Then thiocyanate and the isothiocyanate glycosides. So this is the classification on the basis of the A-glycone moiety that is attached to the sugar. Now we will discuss about certain less prevalent methods as we discussed in the previous lecture. And these less prevalent methods include the classification on the basis of the type of the sugar or the glycone moiety that is present in the glycoside. Say for example, if glucose moiety is present, those glycosides are called as glucoside, and common example of glucoside is senosides that are present in senna. Then if rhamnose sugar is attached, those glycosides are known as rhamnosides, and frangulin is a common example which is found in frangula bark. Digitoxose sugar is present, those glycosides are known as digitoxoside, and digitoxin is a common example which is found in digitalis purpurea. Similarly, if two types of sugars are present, say for example rhamnose and glucose are present, then such glycosides are known as rhamnoglucoside. And rutin is a common example, which is a flavonoid glycoside, is a common example of this type of glycoside when two sugars are present. Now the next less prevalent method is based on the number of the sugar molecules that are present in a glycoside. So if one sugar molecule is present, we call it as monoside, and common example is salicin. If two sugar molecules are attached with an A-glycone molecule, we call them as bioside or bisdesmosides, and biosmin is a common example. If three sugar molecules are attached, we call them as triosides, and digitoxin or digoxin is a common example which is found in digitalis. Likewise, if four sugars are present, we call them as tetrosides, and so on and so forth. Then another less prevalent method which is of classification for glycoside is on the basis of nature of the glycoside. Now on the basis of nature, we can broadly classify these glycosides on the basis of into primary and the secondary glycosides. Now primary glycosides are those which are present in the plant originally, and examples are senosides, which are present in senna as I told you, purpurea glycoside A, which is found in digitalis purpurea. Whereas secondary glycosides are those glycosides which are produced in the plant by hydrolysis of the primary glycosides with the help of hydrolytic enzymes. And the common example of secondary glycoside is digitoxin. Now digitoxin in the plant digitalis is produced whenever the purpurea glycoside A undergoes hydroxylation by purpuridase enzyme that is present in the digitalis. So this enzyme basically hydrolyzes the primary glycoside, that is purpurea glycoside A, to give rise to the secondary glycoside, which is digitoxin. Now this digitoxin further undergo hydrolyzation, a series of hydrolysis reaction to give rise to a glycon moiety and the sugar molecules that are attached to digitoxin. So this was how these glycosides are classified. The prominent ways of classification were based on the type of atom involved in the glycosidic linkage, as well as the type of glycon moiety that is attached to the sugar molecule. And amongst these two, the most easiest and commonly used method of classification is on the basis of glycon. And coming on to the less prevalent method were the methods that involved the type of the sugar that is attached, the number of the sugar molecules, and the nature of the glycosides. So now we move on to the first type of glycoside, that is the anthraquinone glycoside, because I am going to follow the classification of glycosides on the basis of glycon moiety, and amongst those, first I will discuss about the anthraquinone glycosides. Now anthraquinone glycosides are the naturally occurring compounds that are the derivatives of the quinone nucleus, which is 1,4-diketo cyclohexane-2,5-diene molecule. And whenever two phenyl rings are fused with this quinone moiety, we get an anthraquinone moiety, which is 9,10 anthracene dione structure. As you can see on your screens, the structure of an anthraquinone moiety. Now these anthraquinone glycosides are the largest group of naturally occurring quinone derivatives, and in nature more than 700 anthraquinone glycosides or anthraquinone compounds have been identified, and amongst these 700 hardly 200 to 250 anthraquinone derivatives are found in flowering plants, whereas the remaining are found in lower organisms like lichens and fungi. Now these anthraquinones or anthraquinone glycosides, they are not the single compound, but these are considered as the mixture of different types of anthraquinone moieties. And these anthraquinone moieties can be, one is anthraquinone obviously, and second one other moieties are anthrone or anthranol or oxanthrone, and anthrone, anthranol and oxanthrone are the derivatives that are obtained by the reduction of anthraquinone. So anthraquinone on reduction give anthrone, anthrone on further reduction gives you anthranol. So if you look into this chart, you will see that anthraquinone, when it is partially hydrolyzed, you get oxanthrone, and when it is completely, the ketonic group is completely hydrolyzed, we get anthrone, and when the second ketonic group is again hydrolyzed, is reduced, then we get anthranol. And if we go in a reverse direction, that is oxidation of antranol will give you anthrone, and further oxidation of anthrone will give you anthraquinone. Whenever these single moieties like anthraquinone or anthrone or anthranol, when these monomers join together with another monomer, we get dimers of these anthraquinone glycosides. As you can see, I have given example in case of anthrone. When two anthrone moieties join together, we get dianthrone or the dimeric anthraquinone glycoside. Now depending upon the type of the monomer attached in this dimeric anthraquinone, these dimeric anthraquinones can be classified into homodimers and heterodimers. Now homodimers are those dimeric anthraquinone glycosides wherein two monomeric units are same, whereas in case of heterodimeric compounds, the two monomeric anthraquinone units will be different. These are different types of, you can say, different types of anthraquinone glycosides that are found in nature. Now as we have already discussed the classification of the glycosides on the basis of type or the atom of the involved in the glycosidic linkage, these anthraquinone glycosides are also occur as C-glycosides, but the O-glycosidic nature or O-glycosidic form of these anthraquinone is more prevalent in comparison to C-glycosides. And as we have already discussed that these C-glycosides are more resistant towards hydrolysis, and therefore the plants which are having these C-glycosides, and this property of differentiation on the basis of hydrolysis will be used in explaining the chemical tests that are used to detect the presence or absence of these anthraquinone glycosides. Now, amongst various categories of anthraquinones, anthrones are highly unstable, and in plants they generally occur as A-glycon form because their glycosides easily undergo hydrolysis, and normally they occur as A-glycon. And amongst different sugar molecules that are attached to these moieties, glucose and ramenose are the most common sugars you will find that are attached to these anthraquinone A-glycon moieties. Now, coming on to the properties of anthraquinone glycosides, and in most of the anthraquinone glycosides you will find a hydroxyl group attached at carbon 1 and at carbon 8. Now, carbon 3 and carbon 6 are also substituted in some of the anthraquinone glycosides, and at carbon 3 you will find substitution either of methyl group, methoxy group, or alkylated or alkoxy groups, or carboxyl groups. Whereas at position of carbon 6 you may find substitution with hydroxyl group or methyl group or methylated or any kind of alkylated groups are normally substituted, or even phenyl you will find substituted at carbon 6 position. Now, sugars are normally attached at carbon 8 or carbon 6 hydroxyl group if they are present at these carbons, but in case of C-glycosides, sugars are either directly attached to carbon 10 or to carbon 5 also. You may also find C-glycosides when sugar is directly attached to the second carbon of second or the seventh carbon of the anthraquinone moiety. As you can see the example of senoside A, wherein the two anthraquinone moieties are attached at the 10th carbon. Now, as I already told you that glycosides are normally colorless, but exceptions are of anthraquinone glycosides whose color ranges from orange to reddish or reddish brown, and therefore we can say, and since these glycosides are more polar in nature, they are soluble in water or alcohol or their hydroalcoholic mixtures, whereas the A-glycon or the simple anthraquinone moiety is largely soluble in different organic solvents, say chloroform or dichloromethane or ether, and so on and so forth. Now, you will find these anthraquinone glycosides distributed in limited number of families, and most common example of the families having members containing anthraquinone glycoside is Fabaceae, wherein you will find anthraquinone glycoside that are present in different species belonging to genus Cassia, and Senna is one of the most common example. Then in Liliaceae we have already discussed, example is Aloe. Polygonaceae family, example is Rhizum palmatum, that is rhubarb or rumex. Ramenaceae is Ramenis pursiana, that is cascara bark. Anthraquinone glycosides are also found in members of Rubiaceae family, and these are the genera in Rubiaceae family that contain anthraquinone glycosides. Now, these are the examples of monomeric anthraquinone glycosides, and you will see that one is amodin, other is rehin. Rehin is having a carboxylic group at one position, and amodin is having a methyl group substituted at third position. Now, vis-a-vis you will also see their glycosidic form. Amodin 8 glycoside, where the hydroxyl group present at the 8th carbon is substituted with a glucose molecule, and rehin 8 glucoside, wherein again the hydroxyl group at the 8th position is having a substituent with a glucose molecule. And barbeloin, which is present in aloe, is an example of C-glycoside, and here you can see that sugar molecule is directly attached to the 10th carbon present in the anthraquinone moiety. Now we move on to the dimeric anthraquinones, and you will see that these are the examples, common examples of dimeric anthraquinones, senoside A, B, C and D. And as I told you that whenever the two monomeric units are same, we call them as homodimeric anthraquinone, and when these are different we call them as heterodimeric anthraquinones. So if you look into the structure of senoside A and B, here the two monomeric units are same, that is the rehin molecule. As I show you the structure of rehin, it is having a carboxyl group at the third position. Here you can see the R1 position is having a carboxyl group at third position. So this is nothing but glucosylated form of a rehin molecule, and when two glucosylated form of two rehin molecules join together, since both are rehin anthraquinones, senoside A and B are considered as homodianthrones because both monomeric units are same. whereas in case of senosides C and D, you will see that these are the glycosides, dimeric glycosides having different monomeric anthraquinone moieties, and one is the renin moiety and other is the alloamidine moiety, and therefore senosides C and D are considered as heterodimeric anthraquinones. Now hypericin is again another example of different type of dimeric anthraquinone. If you look into the structure of senosides, here the two monomeric units are attached at carbon 10, that is one linkage is there, and you will also see dimeric anthraquinones wherein linkage is present at the third position or at the second position also. But the hypericin is one molecule where you will find that the two monomeric unit are joined together at 3 position, that is C4, C10 and C5. So these are the 3 positions where the two monomeric units are joined together or are linked together, and therefore the hypericin is also known as naphtha dianthrone anthraquinone derivative. Hypericin is largely found in Hypericum perforatum, and the yellow color of Hypericum perforatum flowers is due to the presence of hypericin in these flowers. Now these are the common examples of the plants that contain anthraquinone glycosides. As we discussed, senna is one, aloe is there, rhubarb and cascara. These are the common example one can easily remember, and senna formulations are also available in the market that are largely used to treat the constipation because they act as laxatives. They stimulate your smooth muscles of the colon, thereby increasing the peristaltic movement of the intestine, and this increased peristaltic movements help in evacuation of the bowel. Now we move on to the chemical test for these anthraquinone glycosides, and they are normally tested by using Born-Traeger test, modified Born-Traeger test, potassium hydroxide test and magnesium acetate test. Now Born-Traeger test is a test in which we treat the extract with hydrochloric acid, and then we add chloroform to the extract, and then we add alkali or any ammonia or dilute ammonia solution. So if a pink color or the reddish pink color is generated in the aqueous alkali region, that indicates the presence of the anthraquinone glycosides. So first we treated the plant material, we treat with 5 ml or specified or the required amount of acid. This will cause the hydrolysis of the anthraquinone glycosides. Then we treat that extract with chloroform. So the anthraquinone moieties, the A-glycone moieties will shift into the chloroform layer, and then we treat the chloroform layer with aqueous alkali. So the glycosides or the anthraquinones that are present in the chloroform moiety, when they react with alkali, they will give you slight pink or the reddish color. Now the modified Born-Traeger test is largely used to detect the presence of C type of anthraquinone glycosides. So as we discussed that these C anthraquinone glycosides, they are more resistant toward enzymatic hydrolysis, so they cannot undergo enzymatic or acidic hydrolysis. So the drugs which contain C glycosides, they have to be tested with modified Born-Traeger test, because if you are going to test those plant material with normal Born-Traeger test, then obviously you will get a negative test. So in order to avoid such kind of false negative, you should always confirm the absence of anthraquinone glycosides by performing both tests. One is Born-Traeger and second one is the modified Born-Traeger test. In modified Born-Traeger test, what we do is we treat the plant material or extract first with acid, and then we add ferric chloride solution, which is a strong oxidizing or hydrolyzing agent. So after treating the extract with ferric chloride, the glycosides that are present in the extract, they will get hydrolyzed, and then we separate the A-glycone moiety by treating the mixture with chloroform. So when we treat the mixture with chloroform, the A-glycone moieties which are obtained after hydrolysis, they will immediately get solubilized into the chloroform layer. Then this chloroform layer is separated and again treated with the dilute alkali solution, which can be ammonium hydroxide, or you can add 2-3 drops of ammonia as well. And if you obtain again the pinkish or reddish color in the ammonia layer or the alkali layer, that will indicate the presence of the anthraquinone glycosides. So the bottom line is, if you want to confirm the presence or absence of the anthraquinone glycosides, specifically the absence of anthraquinone glycosides, you should perform both the test, that is Bontrager as well as modified Bontrager test, because only then you will get confirmation that yes, both Bontrager test will give you an indication of O glycosides, whereas modified Bontrager test will give you an indication of C glycosides. Now third test is potassium hydroxide test, or it is also known as alkali test. Now in this, whenever you treat the plant material or the powdered plant material with an alkali, say solution of potassium hydroxide, immediately it will give you a red color. That will indicate the presence of anthraquinone glycosides. Now this alkali test is largely used to locate the accumulation of anthraquinone glycosides in different tissues. Say for example, if you are performing a powder microscopy of a plant material, say senna itself, which contain anthraquinone glycosides, or any other plant material which contain anthraquinone glycosides, and you want to ascertain which tissues are or which tissues contain anthraquinone glycosides, or you can say anthraquinone glycosides are located in which tissues. If you want to identify that, so you prepare your slide using the powdered plant material, and then you add a drop of potassium hydroxide. So the tissues which contain anthraquinone glycosides, they will immediately attain a red color, and from there you can easily identify that yes, these are the tissues which are rich in anthraquinone glycosides, or the anthraquinone glycosides are mainly located in these tissues. And the fourth and the last test about anthraquinone glycosides is the magnesium acetate test, and this is specific for 1,8-hydroxy dihydroxy anthraquinone glycosides, and whenever the extract is treated with magnesium acetate, you get a slight orangish or reddish color that will indicate the presence of 1,8-dihydroxy anthraquinone glycosides. So these are the chemical tests which you can use to detect the presence or absence of the anthraquinone glycosides. Now we move on to the uses of anthraquinone glycosides, and as I have already discussed that these anthraquinone glycosides are known for their laxative action, and they are used to treat constipation. And if you take senna powder, which is normally available in the market, or you take aloe preparation or a rhubarb preparation, and you want to treat your constipation, you can have the prescribed dose of the powder of any of these plants, and you can consume it for relieving of the constipation. And as I discussed that these anthraquinone do not get hydrolyzed in the intestinal region, they immediately shift to your colon region, where they get hydrolyzed by the enzymes, and these the A glycans moieties, since they are responsible for the biological activity, these A glycan moieties or the anthraquinone moieties, when they are released from the sugar molecules, they cause irritation in the smooth muscles of the colon, thereby increasing the peristaltic movement of your GIT, and this increased peristaltic movement helps in evacuation of the bowel, thereby relieving you from the constipation. Now some of the anthraquinone moieties, specifically their A glycan moieties like L-amidin or xanthorin or chrysophenol, they have also exhibited hepatoprotective activity against various chemical models that are used to evaluate the hepatoprotective activity of different test compounds. Some of these glycosides or their A glycan moieties, specifically L-amidin and chrysophenol, they have exhibited very potent kinase inhibitory activity, which has shown beneficial effect in cancer. Though the results are very preliminary, but a lot of work is being done on these molecules for their anti-cancer activities. They have also shown antimicrobial as well as anti-diabetic activities, especially chrysophenol. So friend, this was all about the classification of the glycosides and about the anthraquinone glycoside, that what are these anthraquinone glycosides, what are the different types of anthraquinone moieties that can occur as glycosides in the plants, what are the different plants that contain anthraquinone glycosides, how can you check the presence or absence of these anthraquinone moieties or glycosidic moieties in the plant by performing different chemical tests like bond trigger, modified bond trigger, alkali test, or magnesium acetate test. Then we discussed about the uses of these anthraquinone glycosides. So friends, in the next lecture I am going to discuss about the other classes of glycosides like cardiactive glycosides, saponin glycosides, cyanogenetic glycosides, and so on and so forth. Thank you.